Okay, so now for our engine analysis, we want to go through the engine and calculate the total temperature and total pressure at each station, so that in the end we can calculate the nozzle exit velocities and pressures and determine our appropriate thrust and TSFC values as well. So that we're going to step through component by component, much like we did for the ideal engine, except of course we'll have extra loss coefficients thrown in, and we'll have to account for the fact that each component will have different air properties based on the local temperature of that component. So to begin with, we're going to start calculating right up at the inlet, and we'll need to know, in order to calculate thrust, we'll need to know our inlet velocity of air, and we already know the Mach number, so we need to start off by calculating the speed of sound at our ambient conditions to determine this inlet velocity. So we can say, of course, our speed of sound is going to be equal to the square root of gamma RT, or that's our ambient static temperature. And this calculation is the same as the ideal engine, except, of course, we're going to have to evaluate our gamma. We're going to have to determine that from our curve fit, and we're going to do that using a temperature, our ambient temperature of 383.2 degrees Rankine. So plugging in that accurate value of gamma, we'll have 1.410,436. So a little different than 1.4. Then of course we'll have our value for R, 53.35 foot-pounds force per pound mass degrees Rankine, and our temperature 383.2 degrees Rankine. And we'll need to do a little bit of unit conversion as well. We'll have to say we've got 32.17 pound mass feet per second squared per 1 pound of force. And of course we're taking the square root of that whole thing. So evaluating that out, of course we check our units. We'll have the pounds mass go away, pounds force will cancel out, our Rankines will cancel out, so we're left with foot squared per second squared. So when we take a square root, we'll have units of feet per second. So we'll get 963.12 feet per second. And so our air speed is just, of course, the Mach number times the speed of sound. So 0.87 times 963.12 feet per second. And so we'll have an inlet velocity of 837.92 feet per second. In addition to the inlet velocity, we are also going to want to calculate the inlet total temperature and total pressure, as well as the total temperature and total pressure at the exit of our inlet or diffuser section where it goes into the compressor. So we'll start with temperature or total temperature. The nice thing is that this flow, even though we're going to have losses, it's still going to be treated as adiabatic as it goes through the diffuser. So that means that our total temperature is going to stay constant. So TT2 at the exit of the diffuser, at the inlet to the compressor, is going to be the same as TT1 at the front of the inlet, which is also going to match TTA, our ambient total temperature. So we're going to, in this problem, use a value, our air properties evaluated at the inlet conditions, TTA, which of course match TT2. So our problem is we will have to just guess a value of gamma to get started with, because we don't know what the actual total temperature is going to be. So we're just going to guess that gamma is equal to 1.410436. We'll evaluate our total temperatures and have to come back and perhaps update that guess. So in order to calculate our total temperature, it's just of course going to be equal to our static temperature times 1 plus gamma minus 1 over 2 times our Mach number squared. And so to stick things in there, we'd have 383.2 degrees Rankine times 1 plus that 1.410436 minus 1 over 2, and then times 0.87 squared. Okay, we magically clean that up a little. So if we go ahead and evaluate this, we'll find that our total temperature is going to be 442.72 degrees Rankine. And so since all we did before is just guess a value of gamma, now we're going to need to calculate, based on this new temperature, what is our value of gamma. And so if we put that into our curve fit, we'll get gamma as 1.407103. And so we basically put that in up here again and reevaluate that same formula. We'll get a new total temperature of 442.239 degrees Rankine, and that'll give us a new value of gamma of 1.407130. And substituting that in one more time and recalculating it, we'll get another slightly different TTA equals 442.243 degrees Rankine. But this time when we calculate gamma, we'll find out that it's still 1.040730. So we're pretty well converged on gamma, so we can say, okay, this is going to be our correct value of total temperature at the inlet. And of course, since TTA is equal to TT2, we can say that those are both going to be equal to 442.243 degrees Rankine. Next, we want to calculate the total pressure coming into the inlet, as well as the total pressure at the exit of the inlet where it goes into the compressor. So to calculate our free stream total pressure, PTA, of course we can do that easily based on the Mach number and relate it to our ambient static pressure. So it's that ambient static pressure times 1 plus gamma minus 1 over 2 times our flight Mach number squared to the gamma over gamma minus 1. And what's nice here is, since gamma is only a function of temperature and we've already iterated to solve it, we can just keep using the value of gamma that we determined when we were finding temperature. We don't need to reiterate here. So we can say that our total pressure is going to be equal to 2.99 psia times the 1 plus, and now we have to pull in our gamma, 1.407130. So 1.407130 minus 1 over 2, and times our Mach number, which was 0.87 squared, and of course all of this to the gamma over gamma minus 1. 7130. So if we evaluate that out, we'll get an ambient total pressure of 4.903 psia. And since we're flying subsonic, there won't be any total pressure loss due to shock waves between the free stream total pressure and the front of our inlet. So we can say that PTA is also going to be equal to PT1. And next up, we will want to solve the total pressure at the back of our diffuser, where we will have some total pressure loss due to friction effects. So we were given that our diffuser pressure ratio, pi d, is equal to 0.93, which is equal to PT2 over PTA. This is our overall diffuser pressure ratio. So we don't even necessarily have to know PT1 in this case, but it's nice to know what it is. So we can just calculate PT2 is going to be equal to this diffuser pressure ratio times our inlet total pressure, 4.903 psia. So PT2 is equal to 4.560 psia.